Hello and welcome to this video walkthrough on exploring binary tree concepts using the Titanic dataset in a Jupyter Notebook. In this tutorial, we will be diving into the world of decision trees and exploring various calculations such as entropy, gain, and gain ratio. We will also be creating a decision tree and visualizing it using the BFS algorithm and the PP-tree library. Let's get started. In this cell, we are starting our exploration of binary tree concepts using the Titanic dataset. The authors of this notebook are Piotr Tałksinski and Mateusz Kempa. We begin by importing the Titanic dataset provided by PUT. This dataset will be used for our analysis and implementation of decision tree algorithms. Stay tuned for the next step where we will import the dataset into our notebook using pandas and start our analysis. In this cell, we are setting up the initial steps for our exploration of binary tree concepts using the Titanic dataset. First, we import the necessary libraries, such as copy and math, which will help us with our analysis. Then, we import the pandas library as PD, which will allow us to work with data frames efficiently. Next, we define the path to the Titanic dataset file, which is named titanichomework.csv. We then use the pd.read_csv function to read the dataset into a data frame called data. By importing the dataset into our notebook, we are now ready to start our analysis and implementation of decision tree algorithms using the Titanic dataset. Stay tuned for the next step where we will visualize and explore the data further. #show data. In this cell, we are preparing to display the data from the Titanic dataset that we just imported. This step is crucial as it allows us to take a look at the structure and contents of the dataset before diving into our analysis and implementation of decision tree algorithms. By using the markdown heading #show data, we are indicating that the next block of code will display the actual data from the dataset. This visual representation will help us understand the columns, values, and overall layout of the dataset, setting the stage for a further analysis. Stay tuned for the next step where we will actually print and visualize the data from the Titanic dataset using the print data function. In this cell, we are printing out the data that we imported from the Titanic dataset. The data includes information about passengers such as their passenger ID, P-class, name, sex, age, SIP-SP, PARCH, and survive status. By using the print data function, we can see a preview of the first 100 rows of the dataset, which gives us an overview of the structure and contents of the data. This step is essential as it allows us to understand the information we will be working with in our analysis and implementation of decision tree algorithms. Stay tuned for the next step where we will prepare the data by removing unnecessary columns to streamline our analysis further. In this part of our analysis, we are focusing on preparing our dataset for further processing by removing unnecessary information. Specifically, we are looking at the name column in our dataset, which contains label-like values that do not provide us with relevant information for our analysis. By removing this column, we aim to streamline our code and focus on the essential features that will help us build our decision tree model. Stay tuned for the next step where we actually remove the name column from our dataset. In this part of our analysis, we are focusing on preparing our dataset for further processing by removing unnecessary information. The current cell in our Jupyter Notebook is a simple line of code that drops the name column from our dataset. This column contains label-like values that do not provide us with relevant information for our analysis. By removing this column, we aim to streamline our code and focus on the essential features that will help us build our decision tree model. Stay tuned for the next step where we continue to refine our dataset for analysis. In the current cell of our Jupyter Notebook, we are introducing the concept of entropy in decision trees. Entropy is a measure of randomness or disorder in a dataset. The formula shown calculates the entropy for a given dataset based on the distribution of classes within it. The formula calculates the entropy by summing up the product of the probability of each class and the logarithm of that probability. This helps us understand how much uncertainty or randomness exists in the dataset. By understanding entropy, we can make informed decisions about how to split the dataset in a decision tree to maximize information gain. This concept is crucial for building an effective decision tree model. In the next step, we will implement a function in Python to calculate the entropy of our dataset based on the survived column. Stay tuned for the next part of our analysis. In this part of our analysis, we are diving into the concept of entropy in decision trees. Entropy measures the randomness or disorder in a dataset, helping us understand uncertainty. In the current cell, we define a Python function to calculate entropy based on the survived column in our dataset. We first group the data by the survived column to get the count of decision classes. Then, we iterate through each class, calculate the probability of each class occurrence, and update the entropy value accordingly. By using the formula for entropy, we can quantify the uncertainty in our dataset, which is crucial for making informed decisions when splitting the data in a decision tree to maximize information gain. Stay tuned for the next part of our analysis, where we will explore conditional entropy and its significance in decision tree modeling. In this part of our analysis, we are delving into the concept of conditional entropy in decision trees. Conditional entropy measures the amount of uncertainty in a dataset given the value of a specific attribute. The formula for conditional entropy involves calculating the entropy for each possible value of the attribute and then weighting it by the probability of that value occurring. This helps us understand the uncertainty in the dataset based on the attribute we are considering. By calculating conditional entropy, we can make more informed decisions when splitting the data in a decision tree. This step is crucial in maximizing information gain and building an effective decision tree model. Stay tuned for the next part of our analysis, where we will implement a Python function to calculate conditional entropy based on a specified column in our dataset. In this part of our analysis, we are diving into conditional entropy, a crucial concept in decision trees. The current cell contains a Python function called conditional_entropy that calculates the uncertainty based on a specific attribute value. Here's how it works. The function takes in a dataset in the name of a column as input. It then reduces the dataset to include only the specified column and the survived column. Next, it groups the data by the specified column to count the number of classes within that column. The function then iterates through each class, calculates the probability of that class in the dataset, filters the data based on the current class, and calculates the entropy for that filtered data. Finally, it computes the conditional entropy by summing up the product of the probability and entropy for each class. Understanding conditional entropy is essential for making informed decisions when splitting data in a decision tree. Stay tuned for the next part where we will explore the gain function after choosing a variable A. In this part of our analysis, we are discussing the gain function after choosing a variable A in our decision tree. The formula for calculating gain is straightforward. It subtracts the conditional entropy of the dataset given variable A from the entropy of the dataset as a whole. This formula helps us quantify the reduction in uncertainty or randomness in the dataset when we split it based on the chosen variable A. By calculating the gain, we can determine how effective a particular variable is in splitting the data and making informed decisions in our decision tree. Understanding the gain function is crucial for optimizing the splitting process in decision trees. Stay tuned for the next part where we will implement the gain function in Python and explore its application in our analysis. In this part of our analysis, we are diving into the concept of gain in decision trees. The current cell contains a Python function called gain that calculates the information gained when splitting the data based on a specific column. The function takes two parameters, the dataset and the column name on which we want to calculate the gain. It first calculates the entropy of the entire dataset before the split, E_before, and then the conditional entropy after the split based on the specified column, E_after. The gain is then calculated as the difference between the initial entropy and the conditional entropy. This value helps us quantify the reduction in uncertainty when splitting the data based on the chosen variable. Understanding the gain function is crucial for optimizing the splitting process in decision trees. Stay tuned for the next part where we will delve deeper into the intrinsic function and its application in our analysis. In this part of our analysis, we are introducing the concept of the intrinsic function in decision trees. The current cell showcases the formula for calculating the intrinsic information of a dataset based on a specific attribute. The formula calculates the intrinsic information as the sum of the negative proportion of each class in the dataset multiplied by the logarithm base 2 of the proportion. This calculation helps us understand the inherent information content in the dataset related to a particular attribute. By using the intrinsic function, we can quantify the amount of information associated with a specific attribute, which is crucial for decision tree algorithms to determine the best attribute for splitting the data. Understanding the intrinsic function is essential for optimizing the decision-making process in decision trees. Stay tuned for the next part where we will implement the intrinsic function in Python and explore its application in our analysis. In this part of our analysis, we are focusing on the intrinsic function in decision trees. The current cell contains a Python function that calculates the intrinsic information of a dataset based on a specific attribute. The function takes the dataset and the column name as input, then extracts the relevant columns for calculation. It groups the data by the specified attribute to count the number of classes. Next, it iterates through each class, calculates the proportion of that class in the dataset, and updates the intrinsic information value accordingly. The formula used involves multiplying the negative proportion of each class by the logarithm base 2 of the proportion. This calculation helps quantify the inherent information content associated with the attribute in the dataset. Understanding the intrinsic function is crucial for decision tree algorithms to determine the best attribute for splitting the data effectively. Stay tuned for the next part where we will explore the gain ratio concept and its application in our analysis. In this part of our analysis, we are diving into the gain ratio concept in decision trees. The current cell showcases the formula for calculating the gain ratio, which is a crucial metric for optimizing the splitting process in decision trees. The gain ratio is calculated by dividing the gain of a specific attribute by the intrinsic information of the dataset based on that attribute. To break it down, the gain of an attribute measures the reduction in uncertainty when splitting the data based on that attribute, while the intrinsic information quantifies the inherent information content associated with the attribute in the dataset. By dividing the gain by the intrinsic information, we get the gain ratio, which helps in determining the best attribute for splitting the data effectively. Understanding the gain ratio concept is essential for decision tree algorithms to make informed decisions on attribute selection. Stay tuned for the next part where we will implement a Python function to calculate the gain ratio based on the dataset in a specified column. In this part of our analysis, we are discussing the gain ratio concept in decision trees. The current cell contains a Python function called gainRatio that calculates the gain ratio for a specific attribute in the dataset. The gain ratio is a crucial metric that helps in optimizing the splitting process in decision trees. To break it down, the gain ratio function takes the dataset and the column name as input parameters. It then calculates the gain of the specified attribute by calling the gain function and divides it by the intrinsic information of the dataset based on that attribute, calculated using the intrinsic info function. By dividing the gain by the intrinsic information, we obtain the gain ratio, which is a key indicator for determining the best attribute for splitting the data effectively in decision trees. Understanding the gain ratio concept is essential for decision tree algorithms to make informed decisions on attribute selection. Stay tuned for the next part where we will implement a Python function to calculate the gain ratio based on the dataset in a specified column. In this part of our analysis, we are focusing on creating a decision tree using the create_tree function in our Jupyter Notebook. This function is crucial as it helps us build a dictionary structure representing the decision tree. The function works by recursively splitting the dataset based on the available attributes to find the best attribute for splitting the data effectively. It checks for the entropy of the data and if it's 0, returns a leaf node with the survival outcome. The function then iterates through the available attributes to calculate the gain or gain ratio for each attribute. The attribute with the highest gain is chosen as the best attribute for splitting the data. If the best attribute is age, the function further splits the data based on age values, creating branches for age groups. For non-continuous attributes, it creates branches based on the attribute values. By recursively calling the create_tree function, the decision tree is built step by step until all data is appropriately split into branches and leaves. This process is essential for constructing an effective decision tree that can accurately predict survival outcomes based on different attributes. Stay tuned for the next part where we will delve into implementing the decision tree creation process using the BFS algorithm and pptree library. In this cell, we are defining the create_tree function to build a decision tree based on the dataset provided. The function starts by checking if the entropy of the data is 0, in which case it returns the survival outcome directly. Next, it iterates through the available attributes to find the best attribute for splitting the data. For continuous attributes like age, it calculates the gain using a specific function, while for categorical attributes, it calculates the gain ratio. The function then selects the attribute with the highest gain for splitting the data. If the best attribute is age, the data is sorted by age, split at a certain point, and two branches are created based on the age split. For other attributes, the data is reduced to include only the best attribute and the target variable survived. It then creates branches for each unique value of the best attribute. The function recursively calls itself to build the decision tree step by step until the entire tree is constructed. The output of this cell is the decision tree stored in the tree variable. Stay tuned for the next part where we will use the BFS algorithm to transform the decision tree into a format that can be visualized using the pptree library. In this cell, we are going to use the breadth first search (BFS) algorithm to transform our decision tree into a format that can be understood by the pptree library. The BFS algorithm helps us traverse the tree in a systematic way, starting from the root node and moving level by level to explore all nodes. This process allows us to organize the tree structure in a way that can be easily visualized. By using the pptree library, we can create a visual representation of our decision tree, making it easier to interpret and analyze the branching structure. The pptree library provides a user-friendly way to display hierarchical data structures like decision trees. To implement this transformation, we will define a function called BFS that takes the decision tree as input and recursively traverses it using the BFS algorithm. This function will create nodes for each attribute or value in the tree, organizing them in a hierarchical manner. Once we have transformed our decision tree using the BFS algorithm, we will be able to visualize it using the pptree library, gaining valuable insights into the structure and decision-making process of our model. Stay tuned for the next part where we will execute the code to visualize our decision tree using the pptree library. In this cell, we are defining a function called BFS that uses the breadth first search (BFS) algorithm to transform our decision tree into a format that can be understood by the pptree library. The function takes the decision tree as input and recursively traverses it, starting from the root node and moving level by level to explore all nodes. The BFS function checks if the input tree is a dictionary, and if not, it creates a node in the pptree. It then iterates through the keys of the tree, creating nodes for each key and recursively calling the BFS function on the corresponding subtree. By using the pp-tree library to print the tree structure, we can visualize the decision tree in a clear and organized manner. This visualization helps us understand the branching structure and decision-making process of our model. Stay tuned for the next part where we will execute the code to visualize our decision tree using the pp-tree library. In this cell, we are focusing on splitting the continuous attribute age into two parts to help in building our decision tree. The goal is to find the optimal division point that minimizes the entropy for each part. We start by sorting the data based on age and then iterate through different division points to calculate the entropy for the left and right parts. The division point that results in the least sum of entropy for both parts is chosen as the best split. By determining the best division point, we can effectively split the data based on age and create branches in our decision tree. This process is essential for accurately predicting survival outcomes based on age. Stay tuned for the next part where we will implement the age splitter function and calculate the gain ratio for the age attribute. In this cell, we are defining the age_splitter function to help us split the continuous attribute age into two parts effectively. First, we reduce the data to include only age and survive columns and sort the data based on age. Then, we iterate through different division points to calculate the entropy for the left and right parts. The goal is to find the division point that results in the least sum of entropy for both parts, indicating the optimal split. This division point is crucial for accurately splitting the data based on age and creating branches in our decision tree. By determining the best division point, we can enhance the accuracy of predicting survival outcomes based on age. Stay tuned for the next part where we will calculate the gain ratio for the age attribute and further refine our decision tree creation process. In this video walkthrough, we have covered the process of creating a decision tree using the create_tree function in our Jupyter Notebook. We have discussed how the function recursively splits the dataset based on attributes to find the best attribute for effective data splitting, and how it builds the decision tree step by step. We have also explored splitting the continuous attribute age to help in building our decision tree. In the next part of our analysis, we will implement the decision tree creation process using the BFS algorithm and the pp-tree library. This will further enhance our understanding of decision tree construction and improve our ability to predict survival outcomes based on various attributes. Stay tuned for more exciting insights in the upcoming video. Thank you for watching.